Today I am going to discuss a question related to angular momentum. So let's move to the question. The massless rigid body is pivoted at one end and a mass capital M is at the other end. Originally, the rod on a horizontal table frictionlessly rotate about the pivot with uniform angular velocity such that the mass capital M has speed v. So let's draw a diagram. So it is given that we have a rod, it is a massless and it is pivoted somewhere here, and a mass capital M is attached to the other end like this way, and it is given that it is moving with a uniform angular velocity such that the mass capital M has speed v. So this is speed referring to the linear velocity of the object. The rotating rod collides with another mass capital M at its midpoint. So at the midpoint of this rod, it collides with another mass capital M. So actually the diagram is given in the question, so easily you can identify what is the position of the capital M, which then sticks to the rod. So the most important thing is that this one, after collision, this capital M will stick into this rod. So that means it is undergoing a fully inelastic collision. What is the kinetic energy of the system? Right. So what happens is, after the collision, this one will stick to the rod. So if you draw the second system, you can see this is your massless rod and you have a capital M mass attached here and you have another capital M mass attached here. Right. So we know that both of these are attached to the same rod. That means both of these capital M's should experience the same angular velocity after the collision. So their linear velocities can be different, but their angular velocity must be same, because both of these will move together like this. So they will move together. That means the distance covered by each mass. So if I draw it like this, so this one will have to cover a distance like this, but this one have to cover a distance like this. So basically the linear velocity or the linear speed of this capital M is much higher than the linear speed of this M, right? The midpoint M. But you can see here, when this rotates, the angle subtended by both the objects at the center or the pivot point is same. That means they will experience the same angular velocities throughout the motion. Okay, so we have the clue now. That means after the collision, both will have the same angular velocity. So we will put that one as omega, or we can put it as omega dash, and we can put the initial angular velocity as omega. Okay. So what is our relationship for the angular momentum? So what is the theory of angular momentum? So the angular momentum theory says that when there are no external torques, the total angular momentum of the system is conserved. It is very important, the word system. So the angular momentum of this one only is not conserved, angular momentum of this one is not conserved, but the total system's angular momentum is conserved. That's a very important thing. So what is the equation? You know that we have learned this one. I1 omega 1 is equal to I2 omega 2. So this is our angular momentum equation. So here I represents the moment of inertia, which is the reluctance of an object to move around the circular path or follow a rotational motion. That is the reluctance. And omega is the angular velocity. So now you can substitute here. So if you consider the first case, we know that this rod is massless. So it does not carry any kind of angular moment of inertia, because moment of inertia, we know that it is directly proportional to mass. So if you have covered the theories well, you know that I is proportional to M, mass of the object. So when there is no mass in this rod, that means it does not have any moment of inertia. So you can neglect that. So here you come here and you see now there are two objects. So this one is at rest. That means it does not have any kind of motion. So there's no omega for this one. Therefore, angular momentum of this one is again 0. So only angular momentum is coming from this moving capital M. So we can write it. I can put this one as 1 and this one as 2. So this mass is 1 and this mass is 2. So if you write the angular momentum for the first one, that will be, so this is moving around an external point. So when writing moment of inertia, that you know, when an object is moving around an external point, not around a point on its own, moment of inertia we can write as mr square. So I hope you have covered the theory as well. So when I will repeat the theory again. So when an object is rotating or moving in a circular path around an external point or around an external axis, we can write the moment of inertia as mr square. Right. So we can write the moment of inertia as capital M. We can write the length of this one as L. Then it is ml square times omega plus moment of inertia of this one is angular momentum of this one is 0 is equal to, now we have to write the angular momentum for these two objects. So how do we write? So now we can write for this one, that will be ml squared again times omega dash plus, now this one is also moving the same angular velocity. So this one will have the same angular velocity, that is omega dash. So the moment of inertia will be m L over 2 square times omega dash. Now you can easily simplify this one and you can find omega dash. So we will simplify this one. So here you can cut capital M, it is common for all, you can cut that one, and you have L square common for all, you can cut that one also. And what is remaining? So we have omega here and we have omega dash plus, that is omega dash over 4. So you can calculate 5 omega dash divided by 4 is equal to omega, then omega dash is equal to 4 omega divided by 5. So you know that such that omega is equal to V divided by L. So you can keep this one in mind. Omega is always V over L, linear velocity divided by the moving radius. Right. Now we have to write down the kinetic energy. So how do we write the kinetic energy? So one thing that you can do is, so you can directly write the kinetic energy, because this one has a kinetic energy and this one also having a kinetic energy. So we will write the kinetic energy now. So the kinetic energy is equal to half I1 omega 1 square plus half I2 omega 2 square. So we can easily write down half times I1 means for this one, that is m L square times omega 1. Now here it is omega dash again, because both the angular velocities are now same. So you can write omega dash square plus half I2 means m L squared over 4 times omega dash square. Now you can take all the common terms out. What are the common terms? Half is common for both, ml squared is common for both, and omega squared is also common for both. Take all of these out. Half ml squared, omega dash is this one, 4 omega divided by 5, all the things squared. What is remaining? 1 plus 1 over 4. That is what is remaining inside. Now you can simplify half m L square 4 square divided by 5 square times omega square, omega dash square. This is omega dash, no? Sorry, omega square. So omega is equal to V square over L square. V square divided by L square times, so here you can write 5 over 4. Now you can simplify here. You can easily simplify from here. L square and L square get cancels out. And here you have 1 4 and you have 4 squared here, you can cancel out that. Here you have 5 and you have 5 squared here and you can cancel out that. So what is remaining is the answer. So that is half m. We have v squared remaining here and we have 4 here and we have 5 here. V squared. So these are the remaining parts. Now you can cancel out. Here you have 2, here you have 4. That means you can cut this one, 1 to 2. Then you have 2 over 5 mv square. So this is the kinetic energy of the whole system. Right? So it is not that difficult, the simplification. So there's a bit of simplification. So what I did was I found the final angular velocity because that is common for both objects. Then I write down the kinetic energy. Or you can follow another method, that means in not writing the angular velocity, you can directly write the linear velocity. There's no issue. Okay. So then what we have to do is, then here you have to convert omega dash into the linear velocity. Right. So in terms of v, you can write down the whole expression. Then you can directly apply half mv square. So you can use both these methods, but I prefer this method because it is easy to understand, because both of these will experience the same omega dash, and simplification is also not that much difficult. Right. So I hope this question is very clear to you, and please remember the theories. So the angular momentum theory will be frequently used in your examinations. In most of the questions you have to use this theory. So please understand the theory well and try to do more applications based on the angular momentum. Right, okay. So let's meet in another question like this. So if you have any more questions to be discussed like this, please let me know. So thank you very much for joining with me. So we'll meet you in another video. Thank you very much.